So the next speaker is Yves Pomeau, and his title is here, Dynamics of Self-Gravitating Systems, Variations on a Theme by Michel Hénon.
Thank you. So I'm glad to participate in this conference in the memory of Michel Hénon. And I'll start with a few words on Michel. So the first time I met him was in Nice. There was a small conference organized, if I remember, by this gentleman, who doesn't hear me now, Uriel. And it was organized at the a conference organized at the Observatory of Nice. And I had given a short talk on a short presentation on a subject we have been working on with someone called José Luis Ibáñez. He was a student of Vellard. He was a postdoc at this time. And what he had studied was the Lorentz equation, not the Lorentz attractor, the Lorentz equation for parameters different of the one studied by Lorentz himself. It was in 1976, almost 40 years back. And we had found an attractor, by looking at the computer, etc. On a computer, we had found a strange, what we called at this time, a strange attractor. And this strange attractor was completely different of the one that had been found before by Edward Lorentz. And I made a presentation at this conference in Nice. And during lunchtime, Michel Hénon, who was present at this my talk, he had a hand calculator or pocket calculator. At this time, there was only one kind. There were all Hewlett-Packard. They were quite expensive. And during lunchtime, he managed to find the same iteration, the same an attractor with basically the same properties as the one I had explained before before lunch. He was very, very quick, and very smart, of course. And in the afternoon, we had a discussion with him on this equation, Hénon's equation, or Hénon's attractor, if you wish. And that was more or less what he had done, was the beginning of the Hénon's attractor. So it was a work that was done during lunchtime, so you don't have to organize long meeting, and all the organization of science. When you have very smart people, you don't need a lot of time. So as I said, this attractor, has basically the same global structure. I'm not a mathematician. I'm sure this is not really isomorphic to the one we had found with the Lorentz system, but basically you had the same structure with the horseshoe, etc. And years later, this was a time where chaos theory was very the fashion of the day. And after many years, chaos theory is not so much fashionable now, in at least for physicists like me. And I studied other subjects, and one of the subjects I studied, say in the last 10 years or so, was related to another topic that was also where Michel had a very important contribution, the properties of globular cluster. I'm going to tell what it is, and I think there are other talks on this subject also. And globular clusters was the topic of his PhD thesis. I'm going to explain. And he made very important and very deep contribution on this topic. So as I've been working on this more or less following his inspiration, I chosen as a title Dynamics of Self-Gravitating System, which is another word for globular clusters, at least for me, and Variations on a Theme by Michel Hénon. So I've chosen the word variation by reference, implicit reference to music. When you have many great musicians did work by following a theme that was already in I wouldn't say in the literature, that was already present. The most famous, of course, variation are the Golder variation by Bach, and Goldberg. I think he was a friend of Bach. He was not specifically related to the theme. But so that's why I did choose this title. So, Variation on a Theme by Michel Hénon. So, next. So, Michel had his PhD thesis. That was the year I got to Paris, in 1961. And he has his PhD thesis under supervision of Henri Schatzman. He was his supervisor. And Danjon, I think, was the chairman of his committee, and Delcroix was a member of the committee. And this is an extract of his CV. I turned then to the dynamics of star cluster. He called it star cluster. Now they are more called globular cluster, which became my major subject, 1958 to 1975. In my thesis in 61, I proposed, and I'm going to insist on this point, that the evolution of a cluster under the effect of binary encounters leads to the formation of an infinite density cusp at the center. So this was a CV I think we have found. I owe to Uriel. It was written originally in English, at least the version I have. So, so basically the theme I'm going to work on today, to explain today, are this question of what Michel Hénon called a density cusp at the center of an astrophysical object. So there are basically, as far as I know, two kinds of astrophysical systems where this question of singularity in density is present. This is first, you have the case of globular cluster, which is referred to by Michel in his CV. So you have in a system a large system of about 1 million stars, which are held together by gravitation, and no other force is present. There is no effect, or general relativity effect. And those globular clusters have been of interest for many years because they make a simple many-body system. You have 10 to the 6 million stars held by gravity, a gravity field. So you have a kind of well-defined many-body problem because you know the interaction. It's not like in the ordinary situation in physics where the interaction is not known. In this case, thanks to Newton, we know the two-body interaction. And there is another set of system where this question of singularity in the density is present, which is the interior of stars. We have been working on this topic with Martin. And what I'll maybe say a few words at the end of my talk. At the interior of stars, because of the pressure due to the gravitation, you have a balance of forces between gravitational attraction, and the growth of the pressure. Because when you press a fluid, the repulsion due to the pressure grows. So you have a balance between those two forces. And it happens sometimes that the balance between the two forces is broken because of some reason which is not very clear at the time. And this breaking of the balance of forces can be more or less represented in some simplified equation. And there is, at least this is what people believe, there is a free fall. The winner, when there is a breaking of the balance, the winner, which I think is not clear at all, the winner is the gravitation. So instead of having equilibrium, you have a rush of the matter of the star towards the center, which is due to gravitation. And this rush of matter, at least in some numerical models, ends with the formation of a singularity of density at the center. So this is another case of formation of singularity due to the gravitational interaction. So I'll say a few words on this topic, and because of, in some sense, of the universal nature of gravitation, the equation for the two cases, the density cusp at the center of a globular cluster and at the center of a collapsing star are described by the same equation. So, next. So this is, those two figures are taken from Michel Hénon in thesis, which has been published in Astrophysical Journal. So on the left, you see the curve. You have two more or less Maxwellian, and they are represented at two different steps of time. So you start from a certain distribution of matter in the star, and in the vertical you have the density as a function of the radius. At r equals 0 is the center of the globular cluster. So you see that at two different steps, as time goes, you go from the lower density to the higher density. So as a function of time, the density in the center of the cluster grows. This was observed. This is what Michel observed in a numerical simulation of this gas of stars. You have basically a gas of stars. And on the left, I hope you can see it, you have what he calls a amas artificiel, fake cluster with a central, and this is going to play a central role in my talk, with a central density which is infinite. So what is important to understand is that even though the density is infinite, it doesn't mean that in a gas you have something going wrong. You may have a density going to infinity because just you represent a system of discrete objects by a continuum. And if the mass in the central cusp doesn't diverge, so you have basically nothing very spectacular happening. That was Michel's point. Nothing. This is the center of the cluster. You see, because of the discreteness of the stars, you have an increase of the density, but which is not particularly spectacular. But this represents, when you coarse grain this density, you have a diverging density at the center. This divergence is only an effect of the coarse graining, and I'm going to come back to this point, which was made in Michel Hénon's thesis. So, how to analyze the globular clusters? There have been a lot of work on that, thousands of papers, including some by myself. And you have the first point, which was realized, I think, in the 1930s by Heisenberg and von Weizsäcker, is that you have no Gibbs-Boltzmann distribution for when you have points interacting by gravitation. This is the reason of that is really something which is related to the fact that somehow you have no microcanonical partition function. So in some sense, when you try to normalize the probability density that gives the Gibbs-Boltzmann equilibrium, you cannot normalize this probability density. It is the same issue, if you wish, as trying to define an average density of a point standing on a line. On the infinite, because the length of a line is infinite, you have no average, you cannot define a point at random, or a random number, if you wish, on a line. So what happens in a system where you cannot define a Boltzmann equilibrium? So what one can do is to do numerical simulations. This is something we did years ago. And what happens is that because of the fact that the phase space, which is the phase space as infinite measure, you have, instead of having an exploration in a finite time, or more or less finite time, your system drifts in this phase space with infinite number of dimensions. And so that's the first point. And the other property that this is something which is typical, if you wish, of this gravitational interaction. And because there is no invariant measure, the fact that there is no time-independent measure, every property of your system depends on time, usually with a power law. So the average properties depend on time depending on the point, on the initial condition, and afterwards you have something depending on time or forever. For instance, if you have a system with a few interacting masses, what happens in the course of time is that the potential energy, which has, of course, which is the sum of potential energy plus of the kinetic energy remains constant, but the kinetic energy grows forever and the potential energy decreases forever to minus infinity. So, I saw myself, so if you have a planetary system with a few large planets around a star, at least a conclusion that could be drawn from this kind of consideration is that there is a final evaporation with pair of planets. I don't know if this is what happens, but at least this is a conjecture. So in the long term, you know, the system goes always to the most diverging part of the phase space. So, how to put this in a current scheme? So in his PhD thesis, Michel Hénon took the point of view that self-gravitating clusters are described by the solution of an equation I call Vlasov-Newton. In the literature, it is called either Vlasov-Newton or Vlasov-Poisson.
But excuse me.
Yeah?
Michel Hénon himself has very strongly proposed calling it the genes Vlasov.
The genes?
The genes Vlasov, because it appears in genes before you see it in Vlasov.
No, I'm not claiming. The genes equation?
Genes Vlasov.
Yeah, another third name. Newton is an anteriority. Even though, you know, it has been debated, you know. Maybe we should call it Newton.
Because he's not here to speak.
So let's call it Vlasov genes. Usually it's called either, in literature I know, either Vlasov-Newton or Vlasov-Poisson. Anyway, so this is basically the Vlasov equation, Vlasov-Newton, the Vlasov with a Newton interaction. And so the validity of this Vlasov-Newton equation requires a parameter, because this is not the exact equation for the many-body system. It requires a kind of low density approximation. And the expansion parameter making this valid is the number of stars. So at the first order in the complete theory, you have, at the lowest order, you have the Vlasov, genes, Newton, etc. equation. And at the next order, you take into account the two-body interaction by the Boltzmann collision operator, which is only a correction to the Vlasov equation. So next. So this is what happens. I'll make a few comments there which are not very relevant. The evaporation. So there is, what happens is that because of the Boltzmann collision, because of the interaction, the close encounter between stars, you have a little bit of evaporation. And so if you start from a big cluster of 10 to the 6 stars, after a time, you will have evaporation, because by collision, will have stars falling more and more deeply in the potential and making a more deeply bound potential, and most of the stars will evaporate. And this is what was said at the end of his PhD thesis by Michel Hénon, that the final state, if you start from it will take a very long time, maybe, but the final state of a system of many stars held by gravity will be a deeply bound Keplerian orbit, giving all its energy to the other stars, and the other star will escape the cluster, if there is no physical boundary. And so this, what makes interesting also this, the point made by Michel also was that the mean field approximation becomes invalid where the density is locally too large. So this is what happens in certain solution of the steady solution of the Vlasov-Poisson or Vlasov-Newton or Vlasov whoever equation. So you have for those of you who like So the Vlasov, who know what it is, this is the Vlasov equation, which is an equation for the density of a mass at the position r and with velocity v. So this is a streaming term, and gamma is the acceleration, and this acceleration is computed by using basically the Poisson equation, the solution of the Poisson equation, where rho is the density of mass, of the number density of stars, all with the same mass in the cluster. So it is, you have basically to solve, if you want to solve the evolution of your cluster, you have to solve this set of two equations. So what was noticed, I think, at least by Antonov and maybe by others before, so you have steady solution of the Vlasov-Newton in the spherically symmetric case. They depend on two constants of motion in a spherically symmetric potential, which is a good model for a globular cluster, because globular clusters which are observed, there are about 100 globular clusters in our galaxy. They are seemingly almost exactly spherically symmetric, so it's a good starting point to assume this is an exact symmetry. And if you have two constants of the motion, the square of the angular momentum and the energy, the total energy of a mass in the gravitational field of the cluster. So it is the energy per unit mass, which is half v squared plus phi over r, and you have a system of equations. This equation, you have on the right side an expression of the density in the cluster, which is given by this integral, and you have phi, which appears in this integral here, and phi is also on the right side. So this is an example of what is called a general Lane-Emden equation, where if you assume exact spherical symmetry, you have on the right side a function which is more or less complicated of the potential, and on the left side you have the radial part of the Laplacian in two dimensions. So the result that for a given distribution f of E, you can compute phi, and by solving this equation, in principle, you have the distribution of mass inside the globular cluster. So next, so there is this is a more or less standard problem. So what I did notice, and this is also more or less in Hénon's thesis, not in this form, I should say. So you have a possibility. Let me see. So you have phi naught. You have the potential, gravity potential is. It is assumed that the gravity potential tends to zero at infinity. So you are left with the value of the gravity potential at the center of the cluster. So this may be either a well-defined quantity, like here. When you assume that this integral converges. This is a mass this integral over r converges, or it may diverge. If it does not converge, if this integral diverges, you have a density cusp in the center of the cluster, but as I've shown before, you have a density cusp, but you have this is perfectly consistent with the requirement that the total mass in the cluster is finite and that the total energy is also finite. So you have to play a bit with the exponent. You have an exponent gamma, f of v, etc. So you have a range of value of the exponent. There is an exponent gamma, and the divergence of the potential is given by this. The potential beta at short distance is given by this beta. Beta is a negative number, so you have to have convergence of the density and of the total energy. You have to have beta between 0 and minus 1/2, and gamma larger than 7/2. So that gives a model where you have a density curve in a steady state at the center of the of a gravitational of a globular cluster. this is a good model, which is consistent. So, but what is interesting is, contrary to the case studied by Michel Hénon in his thesis, I assume that this is time independent. And so there are two questions for the singularity. There is a steady state which is time independent, of course. Is a finite time singularity with infinite density at a point a possible state in the evolution of the system? So can it be found as a final result of an evolution? Alors, the answer, and in the case of a steady state singularity, is a mean field. This is what I'm going to explain now. Is a mean field theory, or if mean field or Vlasov-Newton, if you wish, applicable near the singularity? So is it, if there is a divergence of the density, does something special happen near the singularity, as was believed by Michel Hénon, rightly? So the question one I'll discuss in the proceedings of this conference. So if one is close enough to the cusp, the stars, as I said, cannot be considered as anymore as making a continuum, because this is a discrete set of stars, and near the discreteness of the stars becomes important, where between the distance between the center 0 and the radius r, there are a few stars. For instance, there is 1 or 2, etc. Because again, the mass, the total mass of the cusp is convergent. So you need to have a converging integral. So you can always choose a radius where the number of stars between 0 and r is a finite number, and even 0. And so this is in this writing, you have the exponent beta I introduced before. And so you have you take a radius such that between 0 and r star, there are k stars, k being a finite number. So if k is equal to 1, so you have a certain radius, such that there is only one star in the core of the core. So I will, and so the problem, I don't think that I have much time left to discuss that. Basically this is a matching, asymptotic matching problem. You have the continuous limit beyond a certain radius r, and inside the radius r star, one has to solve the k-body problem, and there is a boundary condition on the surface of this inner domain. So this makes a well-defined problem. So in the last minutes of my talk, so I will say just a few words on the problem of collapse in a fluid model. So in the fluid model, the collapse depends on the growth of the pressure as a function of the density near at large densities. So what happens is that if eta, which is this exponent, is larger than 13 over 12, so there is no finite time singularity, because the growth of pressure near the core of the star is strong enough to avoid collapse. And if eta is less than 13 over 12, so there is collapse with a smooth initial condition. So this makes an interesting mathematical problem, which has been studied by some people. But there is as you can see, this number is very close to 1, but it is not 1. It is slightly larger than 1, and so there are some predictions which have been made in the literature which are incorrect, just because they confuse this number, this critical number, with 1. So the occurrence of finite time singularities, so maybe I'll just write the last line, as was understood by Michel Hénon, the understanding of the gravitational problem related to gravitation requires a balanced use of analytical thinking, as he did. In his paper, there is always, his papers are never purely numerical. There is always some smart analytical thinking, and of numerical studies, a message still in order today. Thank you for your attention.
Comments? No? Okay, so thank you again.